All right, everyone, welcome to Physics 6. So this is going to be our first lecture, and we're going to be covering chapter 1, which kind of gives us introduction to overall the concept of measurements, vectors, scalars, and overall, let's say, what physics is as a science. So generally, you can think of this as a very introductory chapter, except let's say maybe the last part where we are looking at a relatively abstract idea of vectors. All right, so all right, so sort of like an overview of the chapter. So we're going to learn about the standards and units and look at some of the unit conversions. Be able to use those measurements, for example, to make calculations and what type of information we gain from those. And at the end, we're going to talk about two types of quantities that we're going to be studying in this class, you can say. So scalars and vectors. So scalars are very simple, very straightforward. So we're going to talk about those. Generally, they represent some kind of physical quantity that represents, can be represented with just a number and a unit. For example, mass. Let's say you just say 5 kilograms, 10 kilograms, and that's it. That's all information you need for the mass. Same with the temperature and things like that. That means, you can say 20 degrees Celsius or 80 degrees Fahrenheit, and you don't really need more information about this quantity. And then we have vectors. These are a little bit more complicated concepts because quantities, because they are not only can be represented with the number, with the unit, but also they come with the direction. So those are directional quantities. For example, velocity is an example of a vector. That means velocity is something that represents how fast you're going and also in which direction you're going that fast. Or you can say then, for example, force is an example of a vector. When you're pushing something, right? So in which direction you're pushing becomes important when you're considering, let's say, the motion of the object. So that's why what we have here is the scalars are one type of quantities, and then the vectors are another type. And the problem with vectors is that, sometimes you might have to add vectors together or subtract or multiply and things like that. And that's where we're going to be learning here to be able to add and subtract vectors, both graphically and analytically, and to be able to simplify vector addition by be able to break them down into X and Y components. We're going to learn all about those. All right, so in any case, so let's start with, identifying that physics as a science, right, is specifically an experimental science. That means one of the things we do in physics, we think of some kind of scenario, right? And maybe like, let's say, hypothesis. And then we come up with some kind of model, you can see, right? So we make a prediction, and then we create a model and hypothesis, from which then we can think of some experiments that we can do to verify that. And once, let's say, experiment gives us the result that we want, or we were predicting, let's say, then we can treat this as a theory, right? That means theory is a hypothesis that has gone through several experimental verifications. All right, so the last one is a law, and physics laws are generally sort of like, let's say, theories that have been let's say, verified in many different circumstances. So for example, most of the laws that we're going to be studying in this class, right, laws of motion and things like that, they are usually, what we call universal. That means, same law is true here on Earth, let's say on Mars, in Jupiter, right? Go to Andromeda galaxy and we expect the same laws to be valid as well. That means, one of the things we talk about, when we say physics law, we're talking about, let's say, our ability to expect the result that basically is given with that law. That means if you have a laws of motion or Isaac Newton's laws of motion, and if I go to Mars and do an experiment, I know what I should expect, because let's say this law tells me that it doesn't matter where you are, what you're doing, you should still get the same result. That means physics is pretty much science, experimental science. And one of the things we're going to learn in physics that a lot of times what we predict, um, let's say, and verify and have, becomes a law, can also be broken at some point because, let's say, we get more information about that specific phenomena. So that's why, for example, Newton's laws of motion were standard for about 300 years, 400 years, until, Albert Einstein came in and, told us that, or showed us that, there are other circumstances where this law doesn't work. And he showed us, for example, that if you're moving really fast, close to the, for example, speed of light, then Newton's laws of motion can break down. So that's why we have this theory of relativity. And relativity basically is a new way of looking at the motion, but at the very, very specific, high speeds. And then we have, for example, quantum physics. And quantum physics also showed that Newtonian physics basically also breaks down when you're considering very, very small subatomic particles. So that's why we have now quantum physics or quantum mechanics, because we cannot use Newtonian laws to describe, quantum phenomena. So that's why, in a way, what we're going to be studying here in this class, in physics 6, basically Newtonian mechanics and thermodynamics and waves. But all of those are considered what we call classical physics. That means everything pre-20th century. And some of those, in a way, doesn't work, let's say, if you're considering some of the new, what we call modern physics, let's say, ideas. So if you're moving at a very high speed, close to the speed of light, then some of those equations and concepts that we're learning don't really apply. But again, that's a very, very small percentage of, let's say, type of science we would do. About everything that we do on Earth, building cars, airplanes, moving, flying, driving, all of those are nowhere near speed of light and nowhere near small at the subatomic particle level. That means for everything other than subatomic level or moving at the speed of light, Newtonian mechanics works perfectly fine. So that's why as an engineer, you're probably going to be using this, if you're an engineer, you're going to be using classical mechanics 99% of the time. All right, so as an experimental science, right, that means you're going to be doing a lot of measurements. And measurements then require, let's say, some standards, right? So what are you measuring? What do you need to measure to calculate something or, get some kind of result? And what we have here is we're going to be learning about 3 main, let's say, standard units that we're going to be using in physics 6. Mainly, it's going to be length measurement, time measurement, and mass measurement. That means those 3 units are pretty much what we call intrinsic properties of our system. That means, in a way, those 3 things are the only things that we need to understand the motion of the object, or how the object will be moving, or what will be the position or velocity of the object at some later time. Because everything in this physics 6 class can be described in terms of those 3 fundamental units: length, mass, and time. So in physics 7, we also learn about new, let's say, fundamental unit, and that's electric charge. All right, so we don't really, talk about electric charge in physics 6, but we're going to be talking about a lot about electric charge in physics 7, because electricity is all in terms of electric charge. But in terms of then those 3 measurements, let's say length, time, and mass, if you take each one of them, for example, length, right? Even length, if you're measuring length as a group, for example, you still might see some kind of disagreement with maybe some of the group members, because maybe one person would like to measure, in inches, another one in meters, the other one in centimeters, another one in feet. So that means, you might have many different ways of measuring, same length of an object. So what we do here is then we describe a system that, more or less a standard system that's going to be used throughout this class, physics 6 and physics 7. That means every time there's a measurement, of length, we want to make sure that everyone agrees to use the same type of measurement, same unit of measurement, and that's based on what we call this SI system, or System International, or another name is a metric system. That means one of the things we do here is the standard, right? SI, let's say system is going to be used throughout, which means that anytime there is a measurement of length, is going to be in meters. Anytime there's a measurement of mass, is going to be in kilograms. Every time there's a measurement of time, it's going to be in seconds, right? So those are the three main, let's say, units that we're going to be using: seconds, meters, and kilograms. So also sometimes we use MKS to represent this type of units. So this is meters, kilograms, and seconds, right? So basically meters, here, kilograms and seconds. You better to do it like that. So MKS units. So sometimes I can just say it's metric system, use metric system, or use MKS units. So when I'm saying you use MKS units, I mean using seconds, meters, and kilograms. Because technically, SI unit can also be in terms of centimeters and grams and seconds. So that's known as a CGS, centimeters, grams, and seconds. Okay, so in a way, both of those are used in an experiment. So depending on what you're experimenting, right? So you can use either MKS, which is again also metric system, or CGS, which is also metric system. It just MKS is the one that we're going to be using in this class. That means, in terms of metric system or SI system, right? We are using meters, kilograms, and seconds. So that's why a lot of times when something is not in MKS units, we're going to need to convert. We're going to need to convert, and you need to know some of those conversion factors. There's a table in the textbook and things like that, and you should be able to use those to get, let's say, some of those conversions. Okay, so some, like, let's say centimeters to meters and things like that, you probably already know, but let's say from meters to miles and all of those things, honestly, let's say you can memorize them, or you can just write it down in your formula sheet and things like that, or a note card, and just, get that whenever you need to convert. Let's say I don't remember some of those conversions myself because I use it and I forget about those. All right, so now let's look at in terms of when you talk about, let's say, length. All right, so the length is in meters, but still, if you measure in meter, let's say, what is a meter? What is the definition of meter? How long is the meter? And obviously, as a scientist, you want to be able to always have some kind of reference, and that's kind of what we have. So that means we have measurements, for example, some kind of measurement standard for length. We have a measurement standard for time, and we have a measurement standard for also the mass. Okay, so for example, here's the second. So let's say, what is a second? Second, originally you can see, right, tied to the length of a day, right? But obviously, some days are longer, some days are shorter, so it's maybe not very useful way of defining a second. What we do right now is we use atomic clock, right? And atomic clocks are exceptionally precise. And what we do here is we take a cesium atom, and we then look at a vibration, certain amount of vibration of a cesium atom, and this number of vibration is considered 1 second. That means whenever this atom vibrates this many times, which is 9,192,631,770 times, this many oscillations is done in 1 second of time. That means whenever we measure this many oscillations, then the clock can, let's say, tick 1 time, right? So that's how we define 1 second. All right, so obviously, you don't have to remember this number and things like that. At least, try to remember, like, let's say, how we define 1 second. Also, let's say a meter, in terms of what is a 1 meter, how long is 1 meter? And it also went through some evolution in terms of, like, let's say, for example, one of the first definition of a meter was take the equator, which is a line that divides Earth into northern and southern hemispheres. So then take the distance from the equator to North Pole, right? And then divide that number by 10 million. All right, so that means obviously, it's very difficult for us to verify something like that, right? So, I mean, that means you're going to have to, if you want to verify, go to the equator, measure the distance from that to the North Pole, and so on and so forth. And Earth is also not a perfect sphere, right? So it's bulgy a little bit. So again, it was good for a while, but then they realized the limitations of this, and it was changed. All right. So now what we have here is, you can see, right, tied to Kaplan charge and counting a certain number of wavelengths. And it's also exceptionally accurate because we are using what we call speed of light. So we know that speed of light, usually written as c, speed of light in vacuum is roughly 3 times 10 to the 8 meter per second. Or technically, more accurately, is this number, 299. That means, 299,792,458 meter per second. And then 1 over that number, right? So 1 over that number is what we consider to be 1 meter. Okay, so that's what we consider to be 1 meter. Okay, and it's, you can see, right, it's so accurate that it loses only 1 second in 30 million years. All right, so that means we don't have to worry about this anytime soon. All right, so same thing with the kilogram. And actually I have, let's say, the outdated version of the definition of kilogram. So the reference cylinder, there was some kind of cylinder. You can see the cylinder over here, right? And the cylinder was basically, kept in Sèvres, France, and it was used as a, like, let's say, a definition of what 1 kilogram is. So imagine if you put it on a scale, something that's twice as heavy as this cylinder, then it's 2 kilograms, 10 times heavier than 10 kilograms, and so on and so forth. But in a couple of years ago, it was actually changed to some kind of physics constant. We call it Planck's constant. So it's based on that. So a little bit more abstract. So basically, we don't use this cylinder anymore as a reference, right, for the kilogram, but a physical constant, which is known as a Planck constant, or based on that, right? So which happen to be a little more accurate. All right, so also one of the things we're going to be doing is to kind of identify or visualize the units that we're going to be using, and also be able to show a very large numbers in a scientific notation of powers of 10, or a very small numbers also in a power of 10. So, and also understand, let's say, how to verify your measurement. So when you measure, let's say, length of a table or something like that in front of you, so maybe that number will be in maybe, like, let's say, a meter or a fraction of a meter, or like, let's say, a few meters maybe, but it can be represented in meters. When you're talking about going from one city to another city, or from one state to another state, most likely meter is not a good unit to use. Then we use maybe kilometers. Okay, so kilo, right? This kilometer, km, is kilometers. That means it's 1,000 meters. So this K stands for 10 to the 3 meters. And most of the time, then we will use that value. So let's say the distance can be reported as 4,621 kilometers, which means, it's 4,621 times 10 to the 3 meters. Or for example, the same number is this, 4.6. The M here is, you can see, right, this lowercase m is a unit, meters. Uppercase m is actually stands for a mega. So this stands for mega, which is equals to 10 to the 6, all right, which is basically a million, 1 million. That means it's 4.6 million meters, all right. So you can see, right, so here's that number, 4.621 million meters. You can write it in terms of scientific, powers of 10, 4.621. So you can see, right, those 3 zeros is basically, replaced by 10 to the 3. Or you can then write this 10 to the 3 as K, which is, kilo, and just write this as, let's say, this comma can be represented as a dot, right? Or 0.62 times 10 to the 3. And at the end, you can also replace, let's say, this, this value in terms of then mega, right? So that means, there are 2 decimal points over there and the 3 decimal points over there. You're just combining them together, becomes 4.6. You know, you can see, right, there's 10 to the 3 there, and there's a 10 to the 3 over there. Okay, so you go from here 1, 2, 3, you put a decimal point, so that becomes 10 to the 3. So 10 to the 3, then you already had kilometers, and then what you have, 10 to the 3, kilometers is 10 to the 3, and 10 to the 3 times 10 to the 3 is 10 to the 6. You just add them together, right? So this is equals to 10, 3 plus 3, so then you get 10 to the 6. All right, so we're going to be using, you know, a lot of those type of, you know, let's say when the big numbers can be represented with the power of 10, or small numbers, you know, especially in physics 7, you know, when we talk about electric charge, it's always a very tiny number. So we need to know how to, you know, use those, let's say, prefixes and abbreviations and powers of 10. And this table can basically help you. In physics 6, we're probably going to go no further than micro. Right, so micro is, you know, this, we use Greek mu, right? So that's for the micro. It's 10 to the negative 6, basically 1,000th of something. Sorry, a millionth of something. And then we have milli, which is then 1,000th of something. So you can see, right? That means if you write, for example, 20 micrometers, this is basically 20 times 10 to the negative 6 meters, okay? So then when you have milli, so let's say if you have 20 millimeters, so then this is 20 times 10 to the negative 3 meters, and so on. Then you have centi, which is 100th of a meter. And then you have, let's say, kilo, then mega, you can see, right? And so on and so forth. So maybe in this class, our range will be this. All right. So make sure you know those prefixes and abbreviations. All right. So let's say I don't, let's say, recommend anything beyond that, you know, if you have to memorize, right? But those, what is it? Those 5 you should, you know, you should try to memorize as much as you can. All right. So if you look at then powers of 10, so let's say here's 1 meter, which is, you know, human dimensions, right? So let's say on average humans are anywhere from 1 meter to, let's say, 2 meters. So let's say, you know, 1 meter, you know, maybe like, let's say average human height is 1.5, 1.6 meters. So let's say, what you have here is, let's say if you're looking at, this is, you know, using yourself as maybe a reference for length. So then you can see, right, 10 to the 7 meters is already, you know, diameter of the earth. Then that means, you know, take 1 and add 7 zeros next to that. Or, you know, 100,000 over 1 meter distance is already diameter of a red blood cell. You know, 10 to the negative 10 is a radius of an atom. 10 to the negative 14, radius of an atomic nucleus. Or you can go further, 10 to the 11, distance to the sun. We'll call this actually 1 AU, astronomical unit, right? Or 10 to the 26, limit to the observable universe. Obviously, you know, we can't even imagine any of these type of numbers, but maybe we can imagine, let's say, maybe like somewhere over there, right? More or less visualize it and things like that. And that's kind of like what we're going to be doing in physics 6. So this is something we'll do in physics 7. So go and look at some subatomic particles. All right, so in terms of then conversions and things like that, right? So you need to, you know, practice a little bit on working on those. So I'll put some, on mastering physics, I'll put some, you know, assignments for you guys to work on, you know, conversions. But I don't really do a lot of conversions, let's say, on the exams and things like that. Maybe on the quizzes, if I give you something in kilometers, you convert it to meters and things like that. So, but remember, in a way, what we have here is MKS units, right? Which means that if you are not in MKS unit in a problem, you need to convert to MKS units and then do the calculation. So sometimes, you know, one, as I said, right? So those are, so let me go back. So MKS units, right? MKS, right? So this is meters, kilograms, and seconds, right? So let me write it in terms of this. So this is actually what we call dimensional analysis. This is meters in, for the length. This is K stands for kilogram. This is for the mass. And the second here is for the time. That means those are the fundamental units that I was talking about. So measurements of length, measurements of mass, and measurements of time. Because everything in this class can be derived from those. So you can say, right? So the derived units, and everything basically we can derive. So for example, let's say speed. Speed, just or velocity, right, tells you how fast you're going, in which direction, for example. So the speed tells you that, for example, you go from, point A to point B. Right. So let's say you have 100 meters distance. Right. So you go from A to B, and that's a 100-meter distance. So that's a measurement of length. Let's say then we put like L is equals to 100 meters. And let's say it took us, I don't know, 10 seconds to go from, A to B, 10 seconds. So those are two measurements, right? Length and time. Well, what we can do then, we can use this to solve for what we call velocity or speed. Let me do speed, because speed just gives you how fast you're moving without any direction. Well, speed. Speed here is a distance over time. See, speed is distance over time, which means you take distance, 100 meters, divided by time, 10 seconds, and what we get here is this. It's 10 meters per second. See, that's the unit for the speed. How many meters you cover during that time interval? Meters per second. So that's why it's a derived quantity. We're deriving it from measurements of length and time. How about if I want to know the acceleration, which is how fast you speed up or slow down? So for that, what you can do here is we can take the velocity, for example, 10 meters per second, and divide it by time. So let's say 10 seconds. And this will be, let's say, 1 meter per second, then divided by 10 seconds, right, per second, so another second. So 1 meter per second, which we write as 1 meter per second square. And this is A for the acceleration. So this is basically the unit for acceleration. How many meters per second you cover each second. Again, it's all based on this units of length, time. All right, so, and everything else. So let's say joule is a unit of energy. We're gonna see that in chapter 7. And joule is a unit representing energy, but it's also same as kilogram times meter square over second square, because it depends on the mass of the object, and length squared divided by time squared. So that means, again, anything can be derived all the way down to the fundamental units. All right, so you can see, right, in the United States, we often encounter measurements in miles, feet, pounds, quarts, in gallons, and things like that. It is useful to memorize one conversion for the displacement, one for volume, and one for mass. And everything else could be reached by converting orders of magnitude. All right, so now that means, whenever we are talking about the length measurement, right? So remember, there are some conversions that you can, memorize, right? So let's say from miles to kilometers. Once you memorize that, then for kilometers to meters, it's easy, because kilometers is 1,000 meters. That means you can just easily go from kilometers to, let's say, meters. It says mass is tricky. And that's because there's a difference between mass and what a lot of people think of the mass, is in, let's say, in terms of what we call British system, right, that we use in the United States. Because a lot of times people confuse mass with their weight. So let's say very often, let's say I would ask, so what's your mass? And they would say, oh, I'm 150 pounds, or 180 pounds. But, I'm not asking for their weight. I'm asking for the mass, but I get answer in terms of the weight, in terms of the pounds. Well, that's the thing. Pound is not a unit equivalent to the kilogram, because pound is a unit of force rather than mass. And that's kind of what we're going to see. See, there's this mass, which we do in kilogram, and there's a pound, which is actually force. And it's not even an SI unit, because in SI unit, units of force here is Newton, okay, not pound. Pound is actually not a metric system at all. It's actually a British system. So pound and feet and inches, those are all British system, and that we are not going to be using so much. These are some conversion factors. So for example, you can go from inches to centimeters. I think this is something that most people know. 2.5 2.54 centimeters, 1 inch. And then, like let's say from inches to feet and feet to, and so on and so forth, right? And here's one that, in a way you can use, which is 454 gram is equals to 1 pound. Okay. So in a way, let's say 1 pound is roughly half a kilogram, And 1 liter is 1.06 quarts. Okay, you can certainly choose a different set and so on and so forth, but this is something, let's say, you can, try to remember, because, once you have let's say feet, you can convert to inch, from inch to centimeters, from centimeters to meters, and so on and so forth. Try to like memorize, so like kind of like one set and then go from there. All right, so this is kind of, let's say, conversion example. But imagine, like, if you're taking the physics class, that means you have taken trig, you have taken, algebra and, college algebra and pre-calc and things like that, and you have, probably no problem with converting like this. But in any case, so here's one example. So we have Alpha Centauri, which is actually closest star to us. It is 4.3 light years away. Now, light year is actually measurements of length, okay, measurements of length. And it also tells us information about the time. So in a way, you can think of like, let's say when the light leaves this Alpha Centauri star, it travels for 4.3 years to get to us, okay? So that's right, so 4.3 years equals time it takes for light to travel that distance. Now we have this equation that I showed you where speed equals distance over time. See, I can rearrange this where I multiply both sides by time. So here I cancel the time. That means I can write as distance, which is, on it by itself on the other side, right? Equals times speed. That means you have already your first equation. Speed equals distance over time, or distance equals times speed. All right, so then let's look at, it says how many kilometers away is this star from Earth, right? So distance equals then time, where time is 4.3 years, because remember, 4.3 light years away distance means that light has to travel 4.3 years to get to us. So the time is 4.3 years, but years is an SI unit or an MKS unit. So we need to convert it. So this becomes then a conversion factor. And what we're using here is this 1 year is equals to 3.15 times 10 to the 7 seconds. So we're using this conversion factor. And obviously, when you're converting from one unit to another, you use a ratio, right? So then we use this ratio. So you can see, right? We use this ratio to convert time from years to seconds. That means we make sure that year is at the bottom. So then you can cancel, right? You can scrub, you cancel from both sides. And then what we do here is, here's the speed. Well, the speed here is then speed of light in vacuum. And remember, I gave you that number, it's 3 times 10 to the 8 meter per second. So then you write times 3 times 10 to the 8 meter per second. But remember, it's asking in kilometers, not meters. So then we use this conversion where 1,000 meters is 1 kilometers. So that's the conversion over there. That means we then take this speed and convert it to kilometers per second. Okay. So then, but when you put everything together and multiply, you can see, right? Years cancel, seconds cancel, meters cancel, and the only unit surviving is the kilometers, and then you multiply everything together and you get this number, 40 times 10 to the 12 kilometers, and that's 40 parameters, so PM. So we don't, we don't really use it so much, but let's say that's the value. That means it's an insanely, distant object. That means if you can travel at the speed of light, which we can't, nothing can travel as, as fast as the speed, it will take you 4.3 years. That means if, let's say right now we travel with our modern technology, it will probably take us hundreds of years, if we can, which we can't right now. All right, so one of the things we can see here is it says your measurement tools have limitations and your reported results need to reflect those limitations. So this is something actually I'm going to be talking about a little bit more in greater detail tomorrow during the, like let's say Wednesday during the lab. So what I have here is then this. So let's say if you're measuring something, you can see, right, you have your tools, but let's say, for example, your measurement can be between the millimeter marks and things like that. So you can see, right, so you have 135 millimeters, but technically the reading is between the millimeter marks. And same thing is here. So then what we do over there, a lot of times we have to estimate. That means estimate the distance between the millimeter marks. And that means, we are kind of guessing what the distance is, all right? So that's right. At the risk of making data feel unwanted, we dare not to report any, our calculation will tell us. So let's say one of the things we do here is divide 1 sig fig by 3. So also like, let's say in terms of sig figs, right? So your calculator will give you 3.3333. All right, so if you report this answer, the reader will believe you have measured carefully to billionth of a unit you are using. That means when you write all those, means that you take into account precision. That means your measurement was also as precise up to, let's say, billionth of a unit, but it wasn't, right? It was 10 and 3. So it's not a billionth of a, let's say unit precise. So it would be wrong, let's say, to report it like that. All right, so then what can happen? It's possible that bolt holes will fail to line up. Well, things like this. So a lot of times what we do, again, I'm going to give you a handout that teaches you some of those things. You're going to have to follow those sig fig rules. There are sig fig rules that you probably learned in college algebra or pre-calc, where when you multiply things together, you go with the least amount of sig figs. When you divide, least amount of sig figs. When you add or subtract, then you go with the least amount of decimal points. So those are the things we'll go over in the lab, in the handout, and I expect that all the lab reports will be based on those rules. All right. So we are ready then to go into this scalars and vectors, kind of part of the chapter. So what we have here is, as I mentioned, we are going to be dealing with two types of, quantities in physics. Scalars are type of quantity that can be represented by a number and a unit. Remember, still anything physical have to have a, let's say a unit. Because for example, when you say 5, well, 5 is just a number. So unless you want to make something physical, you have to, if you want to make something physical, right, you have to include a unit, because 5 is what? Is it 5 meters, 5 apples, 5 kilograms, 5 bunnies, right? I don't know what 5 is until you say, okay, I'm talking about 5 kilometers, or let's say 5, meters, or 5 centimeters, right? Because as soon as you include the units, now I know what you're talking about. 5 centimeters is a measurement of length. 5 seconds is a measurement of time, right? 5 degrees is a measurement of temperature. But 5, it's nothing, it's just a number. So then what we have here is, you can see, right? Quantity that can be described by a number with a unit and doesn't require any type of direction is known as a scalar. Mass is a scalar. Time is a scalar, because we don't need any type of, let's say, unit direction for those. Temperature is a scalar. And scalar quantity can be positive or negative, because you can have negative 20 degrees Celsius, right? So you don't have to, make sure that, say, scalar quantity must be positive. No, it can be positive, it can be negative, depending, let's say, what you are measuring. So, but then you have quantity that cannot be just in terms of number and unit. It has to give you also direction. So those are vector quantities. Okay, so for example, speed is a scalar quantity. It just represents how fast you're going. So let's say when you talk about speed, you can say, right, let's say I was just driving 20 miles an hour, or let's say using MKS units, I was driving 10 meters per second, right? So 10 meters per second, just, information about how fast I was driving. That's the speed, which is a scalar quantity. But then if I want to tell you some kind of, a vector quantity that tells you how fast I was moving and in which direction, I have to also include then a direction in that, information. So for example, if I tell you I was driving 30 meters per second heading north, now I'm giving vector. And that's this guy over here, velocity. Velocity is how fast you're moving and in which direction. Think like this. If somebody comes to you and asks you, let's say, what is the nearest library? And you say, okay, it's about, again, MKS units. Let's say it's about 500 meters from here. Right. So what are you given that information you're giving that person? Well, what you're given is a distance, how far away the library is. So that person can say, all right, so good, 500 meters. But if that person wants to go to the library, the next question will be, where do I go 500 meters from here? That means which direction should I walk 500 meters to get to the library? That means now you have to give 500 meters north or northeast, or some kind of direction involved, right? So for that person to be able to go from where you are to the library, what you can see over here, right? So what you have in this picture here is, let's say this is you, right? And or the person who asking where the library is, and then you have to go to the library. So library is, for example, half a mile from where that person is, but in which direction should you move or walk half a mile, right, to get to the library? So that's why there are a number of things we can do to represent direction. You can say go north, go east, move to the right or move to the left or up or down, right, and things like that. So we're gonna see that in order to talk about this quantity that we call displacement, we need to talk about, how far away something is and also in which direction you have to move. So that's basically what we call displacement. And there's also acceleration and the force. Those are also other quantities that are vectors. That means they are, require two information, some kind of size, right? And, a direction. So that's why the vectors come, so any vector, right, has two components, two parts: magnitude, which we also, we call it its size, and the direction. So any vector comes with those two informations, magnitude and direction. All right. So then another thing we can do here is we can draw those, let's say, vectors. And vector can be drawn using arrows. And let me actually, give me 1 second. All right, so I want to actually, show you in terms of how to draw the vectors. So let's say one of the things, we can do here is to understand that whenever you are measuring something or you're presenting something, you usually need to have some kind of, coordinate system. Usually, like, let's say, let me start with that. So let's say we have a coordinate system. And obviously, the coordinate system that we will be using, quite a lot is the Cartesian coordinate system, okay, where this is the x-axis and this is a y-axis. All right, so now, one of the things I have then, this is, let's say, the origin, which is our reference point, okay? And reference point basically represent a point that we can always use to reference where you are, and also, let's say, information on which side of the reference point, let's say, the object is. So for example, then we have this, what we call object, right? An object, let's say object is then anything that we're going to be keeping track of. So let's say you have a person moving. So then we can say, okay, the person is the object. Or we have a car driving, and we can say, all right, car is the object. Because one of the things we do in this, let's say, maybe like first part of this class, is we use what we call a particle model. So this particle model is simplified model that allows us to ignore object, shape and size. So let's say we have shape and size. And what we're doing here is just saying that we don't care about shape and size of the object. All we care about here is this. That means we have some kind of object, doesn't matter which shape or size it is. So let's say this object is right here, okay? Then I can represent it as a particle, because again, I don't care about its size or shape. I can just represent it as a particle. So maybe like a dot like that, okay? Now, what I have here is then, because I don't care about shape or size, right? That means the object is going to be moving in a very simple way. So let's say it's going to be moving to the right, to the left, up or down. That means I'm ignoring any type of spin or rotation, anything like that. So we're going to learn about all of those in the later chapters. Let's say we're going to have to wait until chapters, let's say 10 and 11 to consider all those things. Right now, we just imagine that it's something that's going to be, let's say, sliding, or even like, or just moving from point A to point B. There's no rotation, no spin, nothing like that, for the object. All right, so then one of the things I want to do is to maybe start with identifying, where the object is. Remember, so one thing is important here is the position of the object. Again, we're going to be learning all of this in the next chapter. I'm just kind of jumping ahead because it's important to, visualize vectors from, it's easier to visualize vectors from this type of, let's say concepts. So let's say position. Then I will take here the position of the object, and I can write, since it's on the x-axis, I can write as x. All right, so, but it's also going to be the, in terms of when you talk about position, right? So there's an initial position. So I can represent then x sub I, x, x naught. We kind of actually use it like 0 representing initial position. And we also have a final position. That means the object goes from this initial position to, let's say, to this final position. And we represent it x sub f, x final. All right. And what I have here is, then you can see, right, this distance from x initial to x final, all right, gives me two information. So let's say if I know that object goes from x initial to x final, then see, let's say I can, visualize that this object is moving to the right, correct? That means in order to get to the x final, it has to be moving to the right. So then what I can do, I can represent that with an arrow. So this arrow then going to be like this, where its length represents the magnitude, basically its size. And then we also have an arrow indicating in which direction it is pointing. All right, so that particular arrow is actually what we call a vector because it gives us some information. For example, if I take this x in x initial and give it a value, so let's say, remember, so this is the position, and this is a position to the right of the origin. Remember, if something is to the right of the origin, any x to the right of the origin is positive, right? And any x to the left of the origin is then going to be negative. That's how I represent positive and negative, x greater than 0 or x less than 0. So let's say this is, I don't know, 5 meters. Okay. That means this is a positive quantity, right? 5 meters, or you could just put plus 5 meters. And let's say this is x final, and let's say, I don't know, let's say this is 20 meters. Okay, so let's say that's the 20 meters then. Then what I have here is then one of the things that we do here that we're interested is the position change. Right, it's a position change. That means object went from initial position to final position. And we call this delta x, which is change in x. This delta stands for change, right? So delta x. All right. Delta x is generally written as final position minus initial position. Okay, final position minus initial position. And you can see, right, if I do this calculation, so this is going to be 20 meters minus 5 meters, then I can say, right, delta x here is equals to 15 meters. Okay, so plus 15 meters, right? Now, this delta x is actually an important quantity, right? So this is known as a displacement. As I mentioned right earlier, right, this displacement is one of those, vector quantities. So this is displacement. All right, so this is displacement. Displacement tells you how far you moved from your starting point and in which direction. Now you can see, right, we moved 15 meters and then we moved 15 meters in this direction. So that's what displacement does. Gives you size, 15 meters, and direction in a positive direction. So then one of the things I can do here is I can then represent that this is a vector quantity by putting an arrow on top of this delta x. That means this quantity, delta x, which is a displacement, is a vector because it has a magnitude and direction by putting this, by putting this arrow on top of it. That means if I come back and I can say, all right, so delta x with an arrow, so this delta x represents this green vector. This green vector is the displacement vector. So its length is what 15 meters represents, that means the length is 15 meter long, and then plus represents in which direction that arrow is pointing, it means to the right. So that's why we have magnitude and direction for any vector. Size, which you can represent in terms of displacement, the arrow, the length of the arrow, and then the arrow gives you the direction. All right, so now here's now, imagine this. So let's say we have, let's say, same person here at x initial equals plus 5 meters. Let me do it like that. Again, that means the position of the object is 5 meters in a positive direction relative to the origin, which means to the right. But let's say this time object goes to this position, right? And this is going to be our x final. Now, what is the position of that x final? Again, I have to kind of, use the little bit of, let's say, scaling, right? So let's say if I'm saying this is 5 meters, then this is in a way almost, double that distance, right, relative to the origin. So I can say this is 10 meters. All right, 10 meters. Now, what is the correct way of representing x final, 10 meters? Well, it's 10 meters from the origin. Let's say this is in the negative side, so negative 10 meters. All right. Now, that means if the object goes from initial position to final position, I can again calculate the displacement, delta x. Delta x will be x final minus x initial, just like before. This time, x final here is negative 10 meters. Initial x is then positive 5 meters. All right, so let me do that. All right, so positive 5 meters. So what I get here is then negative 15 meters. All right, so if I calculate this, I'm going to get negative 15 meters, which means this time, again, I'm getting exactly same 15 meter magnitude for my delta x. But the difference here is I have then this as a direction, negative, which means object with respect to where it was now is 15 meters away again, but in a negative direction. So when I'm drawing this vector should be pointing to the left in a negative x direction. All right, so this is, again, this delta x is 15 meters in its magnitude. That means its length is 15 meters, but now it's pointing to the left. That's why displacement tells you in a way in which direction you're moving, right? Negative direction, positive direction, or to the right or to the left, right? So by looking at the displacement, you can figure out in which direction an object moved and how far away it is with respect to what it was. All right, so that's kind of, what we have. One of the things we can have here is also this. So let's say we start from here. All right, let me use this color. So let's say this is our object, or this is our coordinate system, and this is our object, right? So let's say sitting right here. Okay. So let's say this is the object. And in a way, what I can do here is I can say then position of the object here is 0, right? Because it's at the origin. Okay. So object here is at, initial position, which is, origin 0. But this time what object does is, let's say, object goes from this position to, let's say, that position over here. All right. So then I can say, all right, so then my display, so let's say this is my x, let me put like as x1. Okay. And this is, let's say, 3 meters. Okay. Now, what is my displacement? It's going from there to here, right? So this is my displacement. All right. And let me represent this in terms of, I'm going to say, again, you can label it any way you want. I'm going to label this as A. A is just a displacement going from origin to that x equals 3 meters, which is, again, just given, like, let's say, x1 final minus x0, which is the initial. Right. So what we'll get here is 3 meters minus 0. So I get 3 meters, so plus 3 meters. That means my A has a magnitude of 3 meters and is to the right. And that's what you can see, right? So let's say, all right, so it's 1, 2, and 3. All right, so let's say then after that, the object, you know, stays a little bit and then moves on to another point. So let's say it's right here, x2. And x2, let's say, is maybe 7 meters. All right. That means what I have here is now I have a new vector going from x1 to x2, and this is then that vector. Okay. Now let's call this vector b. Why not? So this is vector b. Let's look at what is magnitude of, or what is the magnitude direction of vector b. All right, so vector b, again, it's a change in position between, you can see, right? It's basically delta x going from 1 to 2, right? In a way. So then what I have here is this is then x2 minus x1. So then vector b here is equals to, so 7 meters minus 3 meters. So it's plus 4 meters. That means it's 4 meters long in a positive direction, which again matches that, right? So it's in a positive direction. It's 4 meters long, which is a little bit longer than vector A, because it's 4 meters rather than 3 meters. It's size. All right. Hopefully you guys are following this. Next will be this. What is then the total displacement going from the origin to the point x2? And this is where we can use this vector addition. So we can use vector addition, which means that I can take vector A and I can add this to vector B. I can just add them together. All right. And what I'm getting here is a new vector. Let's call this R, vector R. We'll call this a resultant. So that's the resultant vector. It's also a vector. Now, one of the things I have here is this. For example, you can see that vector A is given as plus 3 meters. Now, the question here is this. How do I know that this is a, let's say, a horizontal vector or is it a vertical vector? See, I have like vector A and it's plus 3 meters. Okay, so I understand it's a length because it has meters. I understand its size and its direction. But how do I know, let's say, it's a horizontal compared to vertical or compared to z-axis? So this is one thing we can do. We can use what we call unit vectors. So things like this. So we are using unit vectors. Okay, so this is actually very useful. Unit vectors are special vectors that can be used to indicate direction, help us understand the direction. So let's say here's our coordinate system, and mostly we're going to do x and y axis. So think like this. Unit vector is some kind of vector that is, let's say, it has a one unit vector is in x direction. So it's x direction. And it's represented by x hat. We call it x hat. Okay, x hat. Which means if I have some vector, for example, vector A, and I have its magnitude and direction, but see, it's 3 meters plus. That means it's in a positive direction. But is vector A vertical or horizontal? We don't know that if I look at just this, information given. But if I put, for example, x hat next to that, now I know for sure that this is a horizontal vector. Okay, so same thing, for example, B, vector B, right? I can come back to vector B and I can say, all right, so this is also x hat because x hat is a positive x direction, negative x hat, then is a negative x direction. Thing like that, right? Negative x hat. And when two vectors have x hat components, right, you can actually algebraically then add them together. For example, see vector A. Well, vector A is also x hat, right? Because, like over here, right, this vector is, this vector is horizontal. So I can put like x hat over there. So when I'm adding A plus B, I'm saying, okay, A has a magnitude of 3 meters and it's in a, x hat direction, then plus, then magnitude of the vector B, which is 4 meters, it's also in x hat direction. So it's x hat means that it's in the positive x direction, right? That means what I get here is this, 3 meters plus 4 meters, and I just factor out x hat. And what I get here is just 3 meters plus 4 meters. I add them together, I get 7 meters x hat. That means what I have here is this resultant vector is then 7 meters long and is in the x hat direction, which means in the positive x direction. And this vector r is basically then, created by adding vectors a and b together. And I can then, generate this vector vector r, by using what we call tip to tail method. All right, so tip to tail method. We're going to go talk about this again a little bit more, but in the slides. But let's say here I want to kind of break it down for you guys. So tip to tail method. Tip to tail method basically used like this. So you take vectors a and b, and you adding them together, right? So you adding them together to get the resultant. And to get the graphical way of finding this vector r is you put those vectors a and b tip to tail. That means tip of A connected to the tail of B. And that's what you have, right? So you can see, right, in this picture here, I have that. I have vector A, and then the tail of B connected to the tip of A, right? Then resultant vector always goes from your starting point to your end point. In this case, what I have here is this. That's, for example, this is my starting point, right? And this is my end point. So let's say, right, so. All right, so again, so this is my start point, and this was my end point. And this resultant vector goes from my starting point to my end point. So this is that resultant vector. And you can see, right, if I do that, this resultant vector is 7 meters long and in a positive x hat direction. That means it's horizontal in a positive direction, and it's 7 meters long. So yes, as you can see, right, so what we're doing here is basically doing vector addition. All right, so this is probably the easy of the, of the vector additions, where you have two vectors on the same axis, right? So you can just simply algebraically add them together. Sometimes you might have something like this. So let's say here's our coordinate system. And let's say that vector A is right here. And let's say I can write as vector A is equals to, let's put this as 4 meters in x hat direction. Hopefully you guys are already, comfortable with this, 4 meter long in a horizontal positive x direction. See if a vector is 4 meter long in a negative direction, basically to the left, then I would write this as negative x hat, or this negative goes in front of it, becomes negative 4 meter x hat, which means it's horizontal 4 meters, but pointing to the left, right? Okay. But obviously that's, our vector right now is horizontal 4 meters pointing to the right. Then let's say this person goes from this initial position to this position 1, and from position 1 goes to position 2, but like this. Okay, that means here's the, point 2. Imagine you're looking from above, from the, bird eye point of view, right? And then you have a person who's, let's say there's a street like this, right? And there's another street like that. Let's say another street like this. So, person goes to the right and then goes, up, right? In terms of from bird eye view, right? It's kind of like moving like that. So then what we have here is the B vector, which represents a displacement from 1 to 2. I don't know, let's say it's 3 meters, but see, I can't write x hat anymore because this is not vertical. What do I do for the vertical? Well, I put y hat, which indicates it's a vertical vector in a positive direction. Again, so y hat represents positive x direction, right? And so you can see, or you can say, like, let's say in a y direction, if you have in a y direction, so let's say in a plus y direction, it's a y hat. If in a negative y direction, so negative y hat. You can kind of like add those to the, to your vector. That means I have this vector A and vector B, all right? Which means that I still have object, right? Let's say this person goes from 0 to 0.1, walks 4 meters to the right, and then walks 3 meters up to get to 0.2. And displacement, resultant displacement, right, is still sum of vectors A and B. Right, so now what I have here is vector A is 4 meters x hat plus vector B is 3 meter y hat. Now the question is, can I factor out and do still 4 plus 3 meters times, I don't know, x hat and things like that? You can see, right? I can't, right? It doesn't work like that. It doesn't work like that because these are like apples and oranges. You can't just add them together. X hat and y hat are two different dimensions. So you cannot algebraically add them anymore together. So that means you can still represent it like this, but you're stuck. You can't go any further. This is just showing you in terms of the components of this resultant vector. It will be easy for us to understand how to approach and find, let's say, the R in terms of its magnitude and direction if I use right now this tip to tail method. The tip to tail method then allows me to show that here's vector A, then tail of vector B is connected to the tip of vector A, and those are my two vectors. Remember, the resultant vector will be what? Going from the very first starting point to your final point, to your end point. That will be the resultant vector. And that's what I do right now. See, that's what I'm going to do. So this is then my resultant vector. That means the resultant vector is not a one-dimensional vector anymore. You can see, right? It's a two-dimensional vector. So then how do we find its size and its direction? Well, we recognize that what we did here, we constructed a right angle triangle. So this is vector A, this is vector B, and this is vector R. That means in a way what I have here is this side is magnitude of the vector A, which is 4 meters. This side is magnitude of vector B, which is 3 meters. And then what I can do here is I can calculate the other side, right, to get R. Remember, this is basically adjacent side. This is the opposite side. And this is basically the hypotenuse. And because this is a right triangle, I can find the length of the hypotenuse and I can find the angle of this resultant vector. That means we're going to be using then Pythagorean theorem, where the R is going to be R squared equals then in this case A squared plus B squared. So that's why, see, I can't add A plus B together algebraically. R squared equals A squared plus B squared. So that means I have to do R is equals to square root of 4 squared plus 3 squared, which is then going to give us 5 meters, right? And then I can find the direction by using tangent of theta, where it's equals to opposite over hypotenuse. So there will be 3 over 4, and then use the inverse tangent of 3 over 4. And if I'm not mistaken, we should get roughly 37 degrees. Okay. That means I can say then this is 37 degrees above the positive x-axis, and it's a 5 meter long, magnitude for the vector R. That means this is, you can say that this is like a different type, right? This is like second case of the vector addition. So this is when vector A's and B's are, vectors A and B are perpendicular to one another. So if they're perpendicular to one another, then we can, use the Pythagorean theorem and add them together like that. Okay. So, and I guess you can say that the first one that we looked at, this was when you can see, right, A and B are parallel to one another. When they're parallel to one another, you just simply algebraically add them together. Why? Because A and B going to be either X hat or A and B going to be either Y hat, right? So you just simply algebraically add them together. All right. Now that's kind of like, that's the case. That means if you have those two vectors parallel, just algebraically add them together. If you two vectors perpendicular, then you can use Pythagorean theorem to, get the magnitude and the direction of the resultant. Okay, so that's why this vector addition can be relatively complicated if you kind of, have, vectors in, like, let's say the vectors that you're adding, right? They're in different dimensions, right? So, but in this case, there are different dimensions, but at least because they're perpendicular, you can use Pythagorean theorem to find them, to resultant relatively easy. Well, the problem here is when you get something like this. So let's say here's your, again, this, you can say this is case 3, right? So imagine now we have this. Let's say we have an object that starts from here, and then let's say the object, moves like this. Let's say it moves like this. Here's vector A. And then from here, for example, it moves like that. This is then vector B. That means this is starting point, this is point 1. Excuse me. So vector A represented going from 0 to 1. And then this is point 2, which is vector B represented going from point 1 to point 2. So resultant vector is still sum of A plus B, because I can draw that resultant vector. Here's the resultant vector from 0 to 2, remember, from starting point to the final point. Here's resultant vector. But I still want to know this. I still want to know what is the magnitude and direction of this resultant vector. But the problem here is this. A is not parallel to B, and A is not perpendicular to B. That means that two methods that I just showed you above cannot be applied here. We cannot use just a simple algebraic addition or using Pythagorean theorem to add them together, because A and B are not parallel nor perpendicular. Okay, so we have to find a new method, and that new method is what we use, what we call a component method. All right, so this is what we call a component method. Now let's see, what is component method? So I think here's where we can stop here and go back to the slides and just continue from there. All right, so this is what we're gonna do. So remember that vector A that I showed you in the previous, let's say whiteboard. So think like this. So this is this vector A. This is that vector A. So what we do here is we take a vector A, which in this case it's a two-dimensional vector, right? It's a two-dimensional vector. So what I do here is I break it down. So I break it down into components. Okay. So I take vector A and find its projection on x-axis. So this is its projection on x-axis. Then I find its projection on y-axis, and this is its projection on y-axis. So that means I take A and break it down into x and y components. So that means AX is its horizontal component and AY is its vertical component, right? And one of the things we have about vectors is this. See, for example, if I have this vector AY, right, for example, see, if I take this vector and I move it right here, see, I simply move it right here. If I move it without changing its direction and its size, that means this is still the same vector, because it's still pointing up and it still has the same size. That's right. The important thing to understand is this. Vectors are technically independent of the coordinate system, because let's say this arrow, right? If this is upward and if it's 5 meters, it's upwards 5 meters here as well. That means if this one is also up and 5 meters, they're the same vector, because same unit, same length, same direction. They're exactly same vectors. But see, if I move it like here, if I move it there, here's an interesting thing you can see. See, vector AX is horizontal, pointing to the right. Vector AY is vertical, pointing up. Those are two vectors. But the way they're connected at tip to tail, and they are perpendicular to one another. And you can see, right, what we just learned, if you have two vectors connected tip to tail, and then you have another vector going from the very starting point to the final point, then that vector, right, the resultant vector this guy over here is nothing but the sum of the x and y vector. That means the resultant vector is the parent vector A, and ax and ay, the components of the vector A, parent vector A, but the way they are related is this. I can take vector A and I can break it down into its x and y components, because think like this. If you start from here and you go straight along this vector A and to get to this point 2, right? You can do that, right? If you go, let's say, from the origin along that vector A to get to the point 2, then you can, that's one way to get there. But additionally to that, you can also get to that point 2, but first going along the AX and then along the AY, and you still can get to that point 2. That means the sum of AX and AY is equivalent to A, because the end result is the same for both. You go either along A alone, right? Or you go AX plus AY, you're getting to the same position. So that's why. Then one of the things we can say here is this. Vector A can be represented as a sum of the component vectors. That means A is equivalent to AX plus AY. And this is important because what I'm saying here is this, thing like this. So let's say if I have this vector A, right? I can replace this vector A with two vectors where anyways, when one vector is like this, AX, another vector is like that, AY. That means those two replace this guy. All right, that means what I'm doing here is I'm replacing one vector with two vectors. The question is, why would I want to do that? I mean, I'm making it harder, right? I'm replacing one vector with two vectors. But the problem here is this, or the advantage here is this. This is a two-dimensional vector, and it's very, very difficult to work with this. I don't want to work with that. But by using the components of that vector instead of that vector, then I can much easier, to do some calculation. That means I rather use two vectors instead of one, because those two vectors, one is along the x-axis, the other one is along the y-axis. That means individually they are one-dimensional, and two one-dimensional vectors always better any day than one two-dimensional vector. So that's why, what we're doing here is we're basically replacing this guy, which is replacing, right, that guy with those two AX and AY. Okay. And I can always then again relate those with using this equation. Okay. Now, here's what we have. So let's say you are given this. So let's say you start with this. You are given this vector A. Now, vector A, remember, is a vector, so it has to have two things, magnitude and direction. So let's say you are given its magnitude as 5 meters. Now, how do I write the direction? Well, the direction we just learned, x hat, y hat, and things like that, right? And it's good, right? X hat means to the right. And remember, I could have used east, right? Representing to the right, and west representing to the left, and north up, and south down, right? But, how about something like this, vector A? Well, we can use them polar coordinates to represent it. See, think like this. I can easily represent this maybe like, let's say 35 degrees. Always referencing the positive x-axis going counterclockwise. See, if I have positive x-axis as a reference line and go counterclockwise 35 degrees, then I get to that vector, right? That means you can use the polar coordinates, right, this angle theta, to represent the direction. And that's what I have. 5 meters, let's say this is 5 meters, and this is 35 degrees. Then what I have here is when I break it down into components, so this is AX and this is AY, then I can see, right, I have nothing but the right triangle. And the right triangle, if you remember, relates those sides by cosine function, which is adjacent over hypotenuse, and the sine function, which is opposite sine of theta, right? Opposite over hypotenuse. Remember, for us, hypotenuse is A, adjacent is AX, and opposite as AY. So that means, for example, sine of theta equals opposite, which is ay, over hypotenuse, which is a. So I have sine of theta equals ay over a, or I rearrange it, move a to the other side, and it becomes ay equals a sine theta. That means if I have magnitude of a, which remember was 5 meters, and theta of a, which was 35 degrees, I can calculate what is the magnitude of vector ay. Same way, cosine of theta equals adjacent over hypotenuse. Adjacent is ax, hypotenuse is a. Rearrange, then we get this guy over here, which is then 5 meters cosine of 35 degrees. That means I can also find the components from here. All right. That means if you are given the parent vector A and its magnitude and direction, then you can find the component using those two equations. Okay, that means finding the components if you're given A and A, theta A. Additionally, one thing we can do here is this. What if you are, instead of, let's see over here. Instead of A and theta A, you're given components, AX and AY. So if I have AX and AY, can I find the parent vector? Well, yes, we can do that. Because remember, so if I take this AY and technically move it here, remember, it's a vector, I can do that. Vector A here is nothing but this guy, which is the hypotenuse. So this is A, this is AY, and I can then say again, using Pythagorean theorem, A has the magnitude calculated by square root of AX squared plus AY squared, and has a direction that can be found using the tangent of theta equals AY over AX. That means you can use the Pythagorean theorem to find, the magnitude and the direction of the resultant, or the parent vector, right? In terms of using the right triangle. So that's why it's very straightforward way of representing two-dimensional vector in terms of two one-dimensional vectors, or if you have the components of a vector, we can say, right, so this second part, right, represents that. If you have components of a vector, then you can use the Pythagorean theorem to calculate its magnitude and direction. All right, so let's look at this. These are, I give you, let's say, 4 different type of vectors. And one of the things we have here is, remember, so the coordinate system, Cartesian coordinate system, we can break it down into quadrants. And remember one thing, every quadrant gives you different signs for X and Y. Same thing now for the components. Remember, here, positive X, positive Y, right? First quadrant. Second quadrant, negative X, positive Y. Third quadrant, negative X, negative Y. And fourth quadrant, positive X and negative Y. So that's why, for example, if you have a vector A here, right? If you have that vector A is in the 4th quadrant. That means if I find its components, I have to understand that its X component should be positive, Y component negative. And that's what we have over here. See, AX is positive, AY is negative. Why? Because that vector A is in the 4th quadrant. Here's another one. Let's look at this C. Out of order, but that's okay. So let's say this represents vector in a 2nd quadrant. Remember, 2nd quadrant, negative X, positive Y. That means AX is negative, AY is positive. So this one is going to be a negative vector because it's pointing to the left. This one is positive because it's upward. Same way here, 3rd quadrant, remember negative, negative. So both of the components are going to be negative. And finally, the first quadrant, X and Y are positive. So the components are positive. So that's why it's important to understand in which quadrant is your vector. So then when you're doing the components, you get the signs of the components correct. All right, so let's look at then an example. A vector has the components in X direction as 22 meters and in a Y direction as 13 meters. That means we're given the components of a vector. What is the magnitude of the vector? That's for part A. And what angle does this vector make with the positive X-axis? All right, so this is, you can see, right, this was the second part of the type of calculation. That means we are given the components. So AX equals 22 meters, AY equals 13 meters. And our goal would be to find the magnitude of this vector. And you can see, right, so basically we have a right triangle. That means vector A magnitude is equals to AX squared plus AY squared. That means it's 22 meters squared plus 13 meters squared. So vector A here is now going to be 26 meters. Part B is what is the angle. Now, how do I find the theta? Well, can I use cosine of theta equals AX over A, or sine of theta equals AY over A, or tangent of theta equals AY over AX? Which one should I use? Well, all of them can be used at this point, because now I have A. It doesn't matter which one I use, right? All three of them can give me the right answer. So just the standard one is tangent of theta is equals to AY over AX. So let's say tangent of theta is equals to 13 over 22. And if I solve for theta, I should get 31 degrees. But technically, all of those could have given me the right answer. You can try it on your own and see that, verify that. All right, so here's another example. You drive a car 680 feet to the east, then 340 feet to the north. What is the magnitude of your displacement? All right, so let's look at this. And it says also using a sketch, estimate the direction of your displacement. Okay. So here's what we have. And remember, now we're using east instead of X, right? East, north, west, south. So let's say if I have that, then I can say, all right, so then I move 680 feet east. So let's say here's 680 feet east. I don't know, let's call this A. I mean, nothing wrong, right, with that. So let's call this A. I can call it anything I want. Then 340 north. Now I'm identifying this length to be 680. Then the other one is about half of that. So it should be, half the size. Let's call this B. All right, so now what I have here is, it says, what is the magnitude of your displacement? Remember, displacement now would be nothing but this guy here, right? Okay, so this is my resultant, right? So let's say displacement, or I can just call it anything I want. So let's call it R. Well, in this case, what I have A and B are perpendicular to one another. That means R is nothing but square root of 680 feet square plus 340 feet square, and you get 760 feet. Okay. All right, so it says verify your estimate with the numerical calculation of the direction. Okay, so we also, let's say, calculate this theta, which we can do that. You can see, right? So it can be applied to just the displacement as well, like this. So same thing, right? Tangent of theta, inverse tangent of 340 over 680, which is nothing but 1/2. So you get 27 degrees. Now, here's one thing you can do. It's 27 degrees, but we are using east, north, and things like that. So how would I represent it in terms of this north and east? What we do here is this. It's 27 degrees. Remember, we're starting from east, right, with respect to east. So it's 27 degrees north of east. So you can now write it like this, because you go 27 degrees north from east, right, toward north from east. So that's why you write 27 degrees north of east. Same way I could have easily represented like this. So if I do 90 minus 27, right, then I could have represented that, what is it, 90 minus 27 is 63, right? So I could have said it's 63 degrees, but in this case, I go from north toward east, becomes east of north. Those are the exactly same direction for that vector R. Both of them would have been accurate. All right. So again, kind of summarizing, remember, we can add vectors together using this tip to tail method, as I showed, right? So let's say here's vector A, here's vector B, connecting tip to tail and finding the resultant by going from point 0 to the point 2, let's say. This is being point 1. But this can also, tip to tail can also work if you don't stop at 2, but let's say go to another point 3. So let's say here, so you have point 0, going to point 1, then going to point 2, then going to point 3. Then you can use still the tip to tail method, where you can say, right, A plus B plus C, right? So you're adding now 3 vectors together, and then you get to point 3. The resultant is still from your point 0 to your last point, which is point 3 here. That means this is still the resultant vector, okay? That means this graphical method allows you to, add as many vectors as you want, and all you have to do is just go from the initial point to the last point. For example, what if, let's say, if I continue going like this to point 4, and then going like that, back to the origin. Now, what is my displacement? Well, my displacement here in this case will be 0 because I come back to the same starting point. That means I can say then my displacement is basically nothing but 0 because I did a round trip. All right. So you can see, right? So in this case, what I have here is just summarizing some of the things we learned. So we have vector A and vector B connected tip to tail. And then what we're doing, A plus B is equal to some third vector. You can call it R, you can call it C. So let's say in this case, let's be calling it C. This is vector C. This is adding algebraically, or sorry, this is adding graphically. Algebraically, to add this together, we had to use that case 3 component method because A and B, they're not perpendicular, right? So they're not perpendicular, they're not parallel, so we have to use component method. And I'm going to show you, like, let's say, how to do the calculation with the component method, right? So, but the idea here is this. To do this type of calculation, you're going to need to take vector A and take vector B and break it down into components and then work with their components, okay? Work with their components instead of the parent vectors A and B. All right, so here's another, let's say you have vector A, B, and C. So imagine you have those 3 vectors. And you're going to be adding those 3 vectors together. So what is A plus B plus C? Remember, you get some vector D, let's say, as a resultant. Now there are several ways you can do. You can do A plus B plus C, right? Sorry, the resultant actually, this R, vector R. Okay. So one thing you can do, you can say, all right, so I'm going to do vector A plus B, and I'm going to say that this is some vector D, and then vector D plus C, and then that's finally the resultant. Okay, so that's one thing you can do. But it's probably, not very useful unless, let's say, it's required or it's asking you're asked to do that. One of the things you can do, you can say, okay, it's A plus B plus C, and then the resultant, going from the first point to the last point. But what if you do B plus C plus A, or C plus A plus B, or something like that? Will that work? Well, yes, it will work. For example, see, you do B plus A plus C, now the resultant, it's exactly the same vector. The idea is that you can add any way you want. So A plus B plus C graphically is equivalent to B plus C plus A, or C plus A plus B. Okay, you can just add any order you want. You're going to get the right answer at the end. All right. So adding vectors using components is a little bit the hardest one. And I'm going to give you an example on that. So this is then required, several steps. You first need to do a graph where you take and find the components of each one of them. Okay. And then you're going to add X and Y components separately, make a table and, show that X and Y component and then add them separately and then find the resultant vector. So that's kind of like what we have. Because one of the things you're going to do here is when you're doing A plus B, for example, but these are 2 vectors like this, right? So let's say this is vector A and this is vector B. That means they are not parallel. They are not perpendicular. And resultant vector, right? Resultant vector is this guy here. So this is vector r. So to find then magnitude and the direction of vector r, we will put them all in a coordinate system. We will then take a and b. So individually, we will break them down into ax and ay. So we're going to break it down into ax and ay. And then vector b, we're going to break down into bx and by. And we're going to use those to find x and y component of the resultant. That's how we have to do that. That means we're going to break down vector a and vector b into its own components. And then we're going to use those components to find the component of the resultant. Because I can find the component of a resultant by adding x and component of each vector, and then the y component by adding the y component of each vector. Then I can find the components. And you already know how to find the magnitude and the direction of a vector if you have its components, right? That's basically what I did in the last two examples. All right, so the idea here is then, you can see in this, hopefully in this diagram. See, here's vector A. This is my vector A. It's a two-dimensional vector. And then this is my vector B, also a two-dimensional vector. They are not perpendicular or parallel, but I'm going to add those two together, A plus B, to get this vector, vector C. That's my resultant vector, vector C. Now, I cannot directly do this calculation, A plus B equals C. But what I can do here is this. We're going to make a table where we approach this kind of like step by step. First, take vector A. See, I'm taking vector A. And I'm breaking it down into components. This is its x component. This is its y component, right? So at least at this point, graphically. That means what I have here is this. See, in this table, this column gives me all of my vectors, A, B, and C. But what I'm doing is technically A plus B equals C, right? That's what I'm doing right now. So I take vector A and I break it down into components, X component and Y component. And then I make another column where this is X components. And I write down, okay, this is my AX. All right, so remember, what I have here is this. AX is to the right, so it's positive. Remember, vector A is first quadrant. And then here I write another column, and this is Y component. So then I write Y component of vector A, so AY. That means A component, the vector A broke down into its two components, AX and AY. So I write them here. This is my vector A. So I'm saying that instead of A vector, I'm going to be replacing it with its components, AX and AY. All right, so then what I'm going to do here is I'm going to take vector B and I'm going to break it down into components like that. And I can say, right, if I break it down into components, I'm going to get a BX and BY. It's also in the first quadrant, so this is plus, this is plus. Okay. All right, so now what I have here is this. Remember, see, this is vector Bx. I can take that and I move it right here. This is my vector Bx. And see, this is vector Ay. I can take it and move it here. This is AY. And then this is then BY. Okay. Do you guys see that? What I have here is this is vector C. And technically, look at this here. If this is vector C, let me use a different color, maybe like, let's say black. So if this is vector C, see, if I take vector C and if I, find this projection on the x-axis, right? Find this projection on the x-axis, this is the size of the x component of the vector C. But see, that size is the same as this size. That means the x component of vector C is equivalent to the sum of x components of A and B, right? Because see, AX plus BX, and I can add them together, right? Both of them are on the x-axis, is then the same size as vector CX. That means if I go to this column, then I can take these two, add them together to get the x component of this resultant vector. That means I can find the x component, see this is equation 1, right? Find the x component of the resultant vector by adding the x component of the vector a and b. And equation 2 gives me to find the y component of the resultant vector is by adding a y component of vector a and b. That means our goal will be to find those two things. That means in order for me to find this resultant vector c, first I'm going to find its component in the x direction using this equation 1, then its component in the y direction using this equation 2, and then use the Pythagorean theorem to find its magnitude and direction like we learned. So find the hypotenuse size and the theta c, and then you have this, magnitude and direction of the resultant. So that's how we approach this type of problems. That means whenever you have two vectors added together that are neither perpendicular or parallel, we have to use this component method. All right. So here's an example. You have a vector A that has a magnitude of 40 meters and it points in a direction of 20 degrees below the positive x-axis. A second vector B has a magnitude of 75 meters and points in a direction of 50 degrees above the positive x-axis. Right. So we have two vectors, A and B. We're given their magnitude and their direction. Sketch the vectors A and B. All right, so let's sketch the vectors A and B. All right, so here's A, 40 meters, 20 degrees below the positive x-axis. This is the vector A. This is 20 degrees, right? And vector B here is 75 meters, that means longer than this, and it's 50 degrees above the positive x-axis. So maybe, that's not 70, so, or 50, something like this. All right, so this is then vector B. This is 50 degrees. All right, so the question here is, what is C equals A plus B? That means resultant vector when I add those A and B together. Okay. Now, here's one thing I can do. I showed you tip to tail method, but there's also another graphical method. It's parallelogram. So parallelogram method. Which I think this one is also easy. What we do, you just create a parallelogram like this, and then the resultant will be the diagonal line like this, going from where they're connected. That means A and B connected at their tails, and then you create a parallelogram, and then this is vector R. Okay. So now, not vector R, vector C. And you can see, right, even this gives you some information, because this tells me that vector C has to be first quadrant vector. That means when I'm calculating its components, they have to be positive and positive, right? When I calculate Cx and Cy. But let's do that. So let's say what we're given here, part B says using the component method of vector addition, find the magnitude and direction of vector C. So let's do that. So think like this. Remember, we are given vector A, and what I have here is this. It's 40 meters, and the theta here, right, basically is given as 20 degrees. Okay, so it's below let's say the x-axis, right? But let's say right now I can write it as 20 degrees. And I can do this, right? I can write vector B is equals to 75 meters. And then theta B here is theta A, right? Theta B here is equals to 50 degrees. Okay. All right, so this will be the first step to do the graph. Second step will be to make a table. So these are our vectors. So we have A, B, and I'm going to add them together to get C. This is going to be X component. This is Y component of those vectors. Let's look at vector A. So then the X component for vector A will be A will be A cosine theta and the y component will be A sine of theta. All right, so now one thing we know is this. Factor A is in a fourth quadrant, so y component should be negative, so we put that negative over there. B is B cosine theta for its x component, and B sine of theta for its y component.
You done?